stochastic differential equation with Brownian motion. It was a work by Zhu on stochastic near-optimal controls in serial differential conditions, and it was there was the control in the drift part and also the diffusion part. From that work, we tried to do a sort of near-optimal control on a model for drug therapy where we have two compartments, one for cancer cells and one for healthy cells, where we have radiation on the cancer cells, and also there's a little bit proportion that can kill also the healthy cells, where we try to find the sufficient and necessary conditions and do a characterization for this model. In more general work in theory, there is work by Farid Shiroub and Brahim Zerdi on near-optimal conditions in stochastic control of jump diffusions, where they also try to investigate the sufficient and necessary conditions for near-optimal control. So here we have the model that we studied. We have three compartments. The first one susceptible, infected, and also recovered. Here we have the relapse. It's denoted by rho R. And we have the reinfection, where it goes directly contact between between a recovered individual and infected individual will have a sort of relapse into the compartment of infected. So for the mathematical formulation, it's as follows: a system of ODEs, where we have beta is disease transmission rate, U is the recruitment and natural death rate, and we have rho relapse rate, gamma reinfection rate, and lambda the recovery rate from infectious disease. So we try to include a form of perturbation into the model where we perturbated the beta transmission and also the reinfection rate in this model. Therefore, we got the following formulation. And firstly, we try to prove the existence of the global and positive solution, where we have the addition of the three compartments is less than 1. Following those assumptions that we'll need to find the sufficient and necessary condition for near optimal control. Firstly, we try to prove some levels that we will use in sufficient condition as prior estimates for the states of the system and also for the backward adjoint equations related to that epidemic model. So we proved that for a condition where we assume that the Hamiltonian is and G are both convex, we have the following formulation. To get necessary condition for near optimality, also we proved some prior estimates for that, for the state and also for the backward adjoint equations. And we got the following two results. This one is for the backward adjoint equation related to the model. And finally, for the necessary conditions, we got the following result. As a simulation for this epidemic model, so we have characterization and numerical simulation for an optimal control, where we have the performance as G for the expectation integral, where we have here W1 is the weight for the infected size, and W2 is the weight for the treatment strategy included in that model. So the class of admissible control law is written as A, and the value function and the optimal control is defined by phi. And for the characterization, we have the following result for U star. So here we try to simulate a scenario where we have a control And we had three trajectories: for the deterministic one, the stochastic one with jumps, and for the controlled stochastic epidemic model with reinfection relapse. So as you can see here, we have less size in the affected compartment, and that is related to the one on the left is U, where we start the treatment strategy from 0, and after that it goes to 1. Therefore, it related to, as a result, to reproduction number less than 1, which can maybe lead us to have an extension of a disease in infected compartment. So as a conclusion, here we try to find sufficient and necessary conditions for a model with reinfection and relapse. Relapse can model diseases such as tuberculosis and herpes, and also for the infection, it can model some aspects, like when we try to characterize heroin or smoking as an epidemic, that can be included in that model. Thank you very much.
Thank you. We'll have time for a few questions. Maybe I can start. I got a question at the beginning. So when you start talking about this diffusion on zero capital T, what is this capital T? Do you assume that it will go away? Is it the beginning of vaccination? It will disappear or something like that?
Capital T is the terminal time where we have the treatment strategy as the final state that we want to have.
Okay, so you assume that if you still have a lot of people infected at time T, they will.
Yeah, for this problem, we have capital T because we have a finite time.
Yeah.
If we want to include like infinite time, biologically it won't have a meaning, but in that problem, we will include the exponential to include the infinite horizon. But for this one, we include the finite horizon.
It's a finite time, so it cannot be a stopping time, right? So
yeah.
Okay. And in your cost functions, I'm not sure what you have as your what is the objective. So it looks like you got the integral of the number of infected, something like that. So you want to minimize
the characterization or the.
Yeah, in your model, you get your notice. Yeah, when you get your model, you're trying to explain what is the objective function.
Before or after?
I think it was after, maybe it's like equation 13.
This one.
Yeah, so you got this is your objective function.
Yeah.
So you look at the expected value of the cumulative sum of your infected. So you count how many infected people you got. This is your target, right? You want to minimize this quantity.
Yeah.
And the second term is
for the treatment strategy is the weight. We choose here quadratic functions so we can have an optimum for this one, and also W2 is the weight for we can change it depending on how we need to use the treatment strategy.
And you don't have any discount
no.
Here. You don't need it.
No.
Okay. Are there any questions from the audience? Oh, yes.
So you showed at the end a couple of graphs with the results of the different models, right?
Which one? This one?
For infected, for recovered. But those are all based on simulations, right? So
just scenarios to use them to prove that those results.
Yeah, but you mentioned at the end that for example, this type of model can be used in the case of tuberculosis or like that. Do you plan on the future of getting data from somewhere, from cases of tuberculosis and see how the model is looking?
Probably depending on, because for tuberculosis you can use the relapse, but for the reinfection part, it's really difficult to estimate those parameters. So maybe for other diseases or other epidemics like heroin, smoking, maybe you can have that sort of data. But for an epidemic, it's really hard to have that estimation for the relapse and the infection, especially to have those parameters.
But against all the talk.